reiterate a point that you made there. I'm also here to partially share some of the experience that I get through National Instruments in a very diverse group of application spaces, but also to find out what you need from the tools vendor. So I welcome any of your comments after the talk or anytime you catch me in the hallways about what your specific needs are and where you consider market trends to go. And so one of the unique things about being with National Instruments, we work in test, measurement, and control with embedded applications as well. So we get exposure to a very broad range of applications: semiconductors, aerospace, military. Test and measurement is a very broad application. We don't have a single industry segment that represents more than 12% of our revenue, so we get a great deal of exposure in all of these areas. And what my role is in particular is described by this graph. In fact, my job title, Lead User Manager, comes out of the Sloan School of Business at MIT under a Professor Eric von Hippel, who has done 20 or 30 years of research into this. And essentially, the idea is that users innovate. In the case of a scientific instrument, the user always innovates. The first instance of a scientific instrument is always developed by the person who's trying to solve that problem. So my job at National Instruments is to manage the lead user process of innovation, to connect with lead users who are ahead of market trends, who experience needs ahead of the rest of the market, who stand to benefit from innovating, then work with them, support the research, build a business case around that innovation, and then see that all the way through to a product coming out into market. And that's where my role is with National Instruments. And it also gives me the opportunity today to talk to you about a very exciting product concept that I have in mind. And this is inspired by an interesting situation that occurred. About a year ago, I got a new boss, the Vice President of Scientific and Lead User Research. And he was new to our team of lead user research teams. And of course, I'm eager to share with him the value and contribution of this team. So he comes to me with a problem. He says, I've got a research scientist at a very large research laboratory who has a proposed tool he'd like to develop with us. And he connects me with this researcher, and here's what this researcher shares with me. He would like to have a graphical tool that represents a network of embedded systems. Each of these embedded systems is a node in this network, and we'd like to be able to drag and drop each one of these embedded systems and be able to add them or remove them readily from the network. He would also like to be able to have centralized computers and data information transferring between the embedded systems and centralized servers or the cloud. He would also like to be able to have an abstract description of the software that is executing on a node or a cluster of nodes, and it's described in a fairly high-level language. The challenge, he said, was that he was having a hard time getting people at his research teams to communicate outside of their organizational silos, getting mechanical engineers to talk to electrical engineers and vice versa. So he wanted here an abstract language where the domain expert was able to describe at a high enough level language what the cluster of computers was supposed to be doing. And the same thing happens for the communication and network behavior. They would like an abstract model for the communication and network behavior for each one of these nodes. But of course, these are integrating with this real world, with the physical world. And so he would like to have very sophisticated plant models that are modeling complex nuclear processes to be simulated in continuous time, closed loop, with not just one node, but multiple nodes in these networks, and to be able to have very precise and accurate simulation of the network as a whole. So we'd also like to take the plant models, the models for the controller, the model for the network, and derive out of that a series of linear temporal logic equations to be used for formal verification and to be able to formally verify the entire system in simulation. Once the system has been verified, he would like to take these high-level models and automatically synthesize code for each node, as well as the communication packets and the communication schema between nodes. And once you have the synthesized code, he would like that to automatically deploy to the entire network and then be able to automatically generate test cases for the formal verification and validation of the system when the system has actually been deployed. This is the tool he asked me to build, and it's formal verification, validation, network modeling, software modeling, plant modeling, integrated into a single tool for his team to deploy. He'd like to see this go into deployment and be used at the facility by combining 2 engineers and giving them 1 year to complete the entire project. And for all of you here who are experts, you understand how just one part of the tool that he's describing is a significant challenge. my response when trying to deliver this tool and impress my new boss was to look something like this. I want this tool, and I think everyone in this room wants this tool, but there are a lot of steps that it's going to take to get to a tool of this level of complexity. And we're starting to go in that direction now, and so what I'll wrap up in sharing with you is how we are trying to take this excellent idea, which is pretty easy to understand from a conceptual standpoint, and bring it into reality. So when we talk about design methodologies, this is an important thing for us, is we need to know what exactly are the components of the design and what's the process that we're going to follow to bring a cyber-physical system from concept to realization. And this includes everything from testing to simulation, specifying hardware, choosing the correct models of computation, and then how you're going to bring it all together through simulation, model-based design, etc. And the problem here, well, there are two significant problems. The first is that there are still gaps from the scientific standpoint in how these processes are developed. We have a high-level understanding of how these processes work, but I think we need to assign metrics to how does the V approach to design work? How well does platform-based design work from a percentage standpoint or a value standpoint? Where are the hang-ups in model-based design? What percentage of your time and effort should go into each stage? The other part that's missing here is that we put domain experts into each one of these blocks of the design. We put the software people purely in choosing the models of computation without the consideration of what a synchronous versus asynchronous model of computation would do to a control algorithm. The controls engineers focus specifically on the control systems applications, and they don't necessarily communicate. So the challenge is, how do we get domain experts to have a larger view of the system design and be more hands-on from their domain expert into the actual system implementation? Our approach to that has been graphical system design, where we take multiple application spaces and map them through a platform language into multiple hardware targets, whether they be desktop computers, PXI systems, which can have very sophisticated test and measurement components in them, embedded hardware, or open source solutions as well. And an important part of this, especially on the software side, is the ability to integrate multiple models of computation. It's a mistake that often is made where a programmer chooses the model of computation that he or she is familiar with to solve a problem, instead of thinking about what model of computation best fits. And so here we allow for multiple models of computation to be integrated onto a single application with very well-defined rules and semantics. And an important part of this is to say, we don't have all these pieces. If we did, we would have been able to solve my colleague's problem. And so we know that they have very sophisticated multi-physics simulation software, circuit simulation software. We have the ability to integrate with verification validation tools. And my message here is that you have to be able to interoperate with other tools that are out there. And every time you cause the user to use two tools, you're also causing them to have to know two tool sets. And that makes it more difficult, and it also introduces organizational silos. So the tighter the integration, the better the design flow will be. And a couple of tools that we're pushing in this direction, for example, DSP Designer is one that is used for OFDM transmitters. And an RF engineer, who is not a hardware engineer by any means, can describe in a synchronous data flow way an inherently parallel algorithm, which is then mapped down onto FPGAs with a great deal of parallelism. And where we're focusing a lot on right now, and this is with my colleagues at National Instruments Berkeley, is on heterogeneous system design and deployment, where you can have at a high level a graphical view that includes multiple hardware targets, and then the problem is automatically partitioned and deployed on, say, multiple FPGAs, or increasingly we're showing a lot of interest in things like Intel Mic platforms or combined Zeke platforms, which you've seen from Xilinx, which are processors and FPGAs combined together. So how do we map onto these targets? And the important part about this is we're taking the design process from being traditionally requiring large teams with a great deal of domain experts who may not communicate effectively across each other, to where you have the domain experts closer to the implementation and working very, very closely with the system designers. So this is the vision that we have at National Instruments. Our goal is to equip scientists and engineers with the tools to solve some of the world's greatest problems. So thank you very much.
Time for some questions.
That's an excellent point. And I agree with you to the extent that you're definitely going to take a performance hit every time you move up a layer of abstraction. I don't necessarily think it has to be a heavy performance hit. To the extent that C has been a suitable abstraction for embedded systems. But if you need to get into the more precise timing, then assembly is going to be the language you're probably going to use, or at least have a good understanding of your compiling technology. But you're correct in that every time you ascend a level of abstraction toward the system-level design platform, you may be taking a hit in performance. And our goal is to try to shrink that as much as possible. We do benefit from things like Moore's Law, and we have seen abstractions like C and languages on top of that have been successful for high-performance situations. So another area that we're able to leverage is, for example, data flow is an excellent model of computation for an FPGA. And so they're using the correct model of computation without having synthesis in between allows for very effective performance and also very tight timing onto an FPGA platform. It's something that has to be tuned, though. And eventually what we want to do is be able to let people speak at the high level about their application, but where they need the type timing and precision is where you have to integrate or interoperate with the other technologies that give you that lower level control. But the goal should be to try to put as much of the design in the high level as possible.
So many of the attendees here work on real-time systems, and could you elaborate where real-time systems technology, like scheduling, RTAS, execution time analysis, that kind of technology fit into this vision?
So especially on our embedded controllers, this is something that's quite important. FPGAs are something we leverage heavily for exactly that reason of precise timing. So you can actually draw a loop in a graphical design environment which has guaranteed single cycle accuracy. When it comes to working in real-time operating systems, a lot of the times our customers may not know what that is. So what we try to deliver to them is an abstraction on top of that. We sit on top of real-time Linux or VxWorks or FarLab or sometimes even Windows to try to get real-time precision. When it comes down to the embedded controllers, what we try to do is give timing loops that behind the scenes there's some sophisticated timing engines that are running, but from a high level, what they see is a loop that's going to execute iteratively, and it is going to have a fixed period, and here's why, and then they can have a concurrent loop drawn right next to that without having to worry about the understanding of how a kernel works or the complexities of having to do threaded programming. Now the side effect of that is that you may not have as deep an understanding of what's going on underneath the hood, but your design productivity goes up significantly, as well as your ability to reason about the behavior of concurrent software.
I just quickly wanted to comment, and now I almost forgot where I was. Oh yes, this was on one of the slides I didn't show, but I think that one of the things that I think is important for this community is that we should actually look at simpler architecture, hardware architectures, right? And we should really start maybe thinking even about dropping all this idea of task scheduling and whatnot. Build everything single tasking on very simple single core, or on a single core, and just give that entire core to a certain task. And then you can do away with a lot of the scheduling issues that you actually have to deal with. All this preemption stuff goes away. Of course, I'm oversimplifying here, but think about it. When Jeff said, if we got FPGAs, we have complete control over how fast something executes at a microsecond, nanosecond level. Right? You can get there even with general purpose processors if you're willing to use very simple architectures. And maybe we should move away from all the complexity that's been introduced for, say, enterprise software, business software, and get back to where we were. And just think in terms of parallelism, like FPGAs.
So I have a quick question for both Peter and Jeff. So I would say among the audience here, we pretty much use a lot of NI, a lot of MathWorks, but we are from the user perspective. So say a lot of the research groups are developing tools, they're developing new methodologies. Is there a way for them to work with you or someone in MathWorks or NI to say, well, can we have a prototype integration, but under the hood? Not just from the interface that you expose. Are there interfaces that allow them to really integrate or replace certain modules or extend certain modules?
So I'll answer first, and then I'll let Peter answer on his side. So the one great way to do this is to get a business card from me and talk to me about your particular idea, because this may be something that we are actively researching, would love to know more about your expertise in areas in which you can contribute. This has also been a big push for us to open up a platform where people can design more sophisticated plugins on top of our tools, understanding that there's going to be a lot of innovation that's coming from users and from the community. And you're going to see coming from us in a fairly short order this kind of modification framework that's going to be much more amenable to exactly what you're describing.
So I think the same answer. Get my business card, and then we should talk about it. That said, I would like to make a plug though. I started this program at MathWorks for summer research internships. We're doing that this year for the first time, and this is really getting an internship, a 10-week internship on site at headquarters at Natick. And this is not going to be someone who's going to just get their feet wet in their code base, but this is somebody who's actually going to be able to take their research and try to see how it could fit into our products and really our code base. And so we're doing that for the first time this year, and if that's successful, then we're hopefully going to extend that. But that's one way to try and see if you can